Swayam Prabha. Digital India. Educated India.
So in this lecture, we look at the concept of active methylene group. We've already seen some glimpses of this in some of the previous lectures, but now we'll try and understand this concept a little better in terms of acidity and pK and so on. Okay, so the first concept that we need to understand is acidity. So if we take an acid AH and put it in water, then if it's an acid, then it's going to equilibrate to produce H3O plus and A minus. And the important concept here is that the position of this equilibrium, is dictated by the stability of the conjugate base, which is A minus. So now the way we would experimentally determine the stability is to measure the equilibrium constant. And the equilibrium constant is nothing but the concentration of H3O plus multiplied by the concentration of the conjugate base divided by the concentration of the acid and water. Okay. Now, it's really important that we understand this because, the conjugate base stability is the primary or the most important factor for determining the strength of an acid. Now, what we know from our many discussions previously in other courses as well is that the water concentration here is so large. It's 55.56 molar, and in very dilute solutions this concentration is not going to change. So therefore this concentration of water is more or less a constant, and so we define a new constant which is known as the acidity constant Ka, which is nothing but the concentration of H3O plus multiplied by concentration of A minus divided by the concentration of the acid. So if you see here, the stronger the acid is, the more stable the conjugate base, the concentration of A minus is going to go up. So the equilibrium will be more towards the right. So higher the Ka value, the better the acid is. Now the problem or the situation is that we are going to be dealing with numbers such as 10 power minus 3, 10 power minus 4, 10 power 2, 3 or things like that. So that's not very easy or very convenient for us to compare. So another parameter is used, which is nothing but pK. pK is defined as the negative log of the Ka. And because this minus sign is there in this definition, the larger equilibrium constant, that is Ka, the larger the equilibrium constant Ka, the better the acid is. That's what we learned. But it inversely sort of correlates with pK. So pK, the smaller the value of pK, the better the acid is. So again, this is a sort of a refresher of what we have done in the past. Now with this background, let us look at some table of pK. So we start from the bottom. So here is the pK of an alkane is really small. It's basically not measurable even. The value is 10 power minus 50. The Ka is 10 power minus 50 and the pK is about 50. Now, as we go up this table, we find that the pK values are becoming lower. And so the benchmark value that we try to look for is the carboxylic acid, which is around 5. Now, let's look at the next molecule here, which is nitromethane. So nitromethane, whose structure I have drawn here, has a nitro group attached to CH3, and this, as you know, is a strongly electron withdrawing group. So if it undergoes deprotonation, that is, it's in equilibrium with its anion. Now the anion, one can draw a resonance form where all the participating atoms have an octet, and so this is a fairly stable resonance form, and therefore one can suggest that the conjugate base is quite stable. So therefore nitromethane, is being a strong acid, is actually quite understandable. If we go down this table, I think we have already looked at amides, aldehydes and ketones and esters. The next molecule that we're going to look at is the nitrile. So nitrile is or a cyano compound is a very interesting molecule. So the carbon here is sp hybridized and the nitrogen is also sp hybridized, and so there is a triple bond over here. All right. Now once the nitrile undergoes deprotonation, it forms this anion, and this anion again one can draw, a resonance form where this negative charge is actually delocalized across these three atoms. Now this makes the molecule certainly more acidic than methane. So if you compare it with methane, it is certainly more acidic. But this conjugation and the resulting stability is not as high as what you would achieve with, let's say, a ketone. Okay, so therefore, there's still a difference between a nitrile and the ketone being more acidic. The next compound that we look at is not present normally in these pKa tables, but it's an important compound nevertheless, which is basically a sulfone. So sulfones are also acidic and they can be deprotonated. The pKa values are somewhere between 28 and 31. And so once you deprotonate it, you get the CH2 minus, and then the CH2 minus can delocalize and produce this kind of a anion. So here, if you notice, the negative charge is on an electronegative atom, which is oxygen. So therefore, this can also be an acidic, that is, sulfones can also be acidic. One comment here is that the sulfur, the hybridization here, and it's lower in the periodic table. So the overlap here is not very good. So if I compare this with a carboxylate or something similar to that, the overlap between the orbitals is not as good, and so the stability afforded by that correspondingly is not very high, and therefore the pKa value is substantially higher than what we would expect with a ketone. So with that, now let's look at the concept of active methylene. So active methylenes is usually referred to when you have the ability to have very strong electron withdrawing groups on a particular methylene carbon. So this is we were discussing about methyl. Now here is a methylene group, which is an active methylene group. So if you see here, this is a diketone and the pKa value is about 9. So if I take a monoketone, that is just a simple ketone, the value is around 20. So there's a substantial lowering of pKa values and increasing in acidity. And as you can see here in this table, there are a couple of other examples where you have a ketoester and a diester. These are things that we will look at in more detail shortly. So one of the ways in which we understand the extremely good acidic properties of these active methylene compounds is because if you do a deprotonation on this, you get this enolate. And once you get the enolate can actually nicely delocalize and produce another resonance form as shown here. And so in essence, it's actually a resonance hybrid that we are going to deal with, which is nicely delocalized across 1, 2, 3, 4, 5 atoms. So with this, you can sort of understand why these compounds, which are known as active methylene groups, are quite acidic and how we can use them later. We will discuss later about how you can use them to exploit in synthetic chemistry.